Hello and welcome to the solar power presentation. My name is Khawarniyal. I work for Tawana Energy and we shall be talking about solar power. The topics we'll be discussing include solar cells, panel specifications, what are charge controllers, uninterruptible power supplies, which is UPS, inverters, the difference between variable frequency drives and solar pump inverters, and a little bit about maximum power point tracking. So let's start. This is a picture of a solar cell. It is something that converts sunlight into electricity. A lot of these combined together make something called a solar module. We also call this a solar panel. The solar cells, they've got basically they're made out of silicon, and they've got phosphorus doped silicon. That means there's a little bit of phosphorus in this layer, and this one is boron doped. That means there's a little bit of boron in this layer of silicon. And here's how they actually make electricity. Light, which is like photons or like units of light, they actually strike this place, and then the electrons get released and they move through this wire through the load to this side, which is the back side is the plus side. And we won't be going into all the details of how this quantum mechanics works, but it's just a simplified version. Then you can put a lot of the cells in like a battery, like you have multiple batteries connected in line in series with each other, so that actually increases the voltage, and you can put the panels in parallel to increase the current. So basically you've got cells which go into modules which combine together to be called a group of modules is called a solar panel in some cases. And a lot of solar panels are also arranged in arrays, which is called a solar array, which is like a lot of thousands of solar modules in a large field. This is what one of the stickers of the backside of a solar panel looks like. It has some of these items like PMPP, UMPP, UOC, and some numbers. We'll be explaining what each of these mean. P represents power, and this MPP means maximum power point. So PMPP means the power at the maximum power point. U represents the voltage. Don't ask me why the U is there. It should be a V, but they use a U. So UMPP, it represents the voltage at the maximum power point. IMPP, I is used for current. They don't use A or C, which is like, don't know why. Anyway, you got IMPP, which represents the current at the maximum power point. Then UOC, which is the voltage at open circuit. Open circuit is when the two wires, the plus and minus coming from the panel or module, whatever you prefer to call it, are not connected to each other. If you do connect the two wires together, you would create something called a short circuit, and this ISC is the representation of the current that will be going through the wire. Don't do this for more than a few seconds if you actually do short circuit the solar panel. Then in some cases, the solar panels might also have other than UOC, they might have like IOC and VUSC. That means the voltage at short circuit, and also they might give you the current at open circuit, which would be written as IOC, and the voltage at short circuit would be written as USC similarly. So as we mentioned, PMPP is the maximum power point, and it is the maximum power that can be drawn from the panel at that time based on the amount of light that is striking the panel. Voltage is the voltage at the maximum power point. That means that is the voltage you will have to set your inverter to get the maximum power out of the panel at that time. Similarly, that is the current is the amount of current you will end up receiving if you set the correct voltage at the maximum power point. And the UOC is a voltage open circuit, as we mentioned. and ISC, which is a short circuit. That means if you do short circuit the wires, the maximum current will be going through, and that is called the short circuit current. So now we'll explain a little bit about volts. Volts is sort of like the pressure inside the wire, and the faster, the more the voltage, the more the pressure, and therefore the electrons move faster through the wire. Amps is like counting how many electrons are going through in a second, and that sort of gives you an idea of, that's called current, which is the amount of charge or the number of electrons going through the wire at within a second. Think of it like a highway. If you've got a lot of cars, each car represents like an electron. If you've got a lot of those cars going through the wire, that would mean a lot of amps are going through. If they're going faster on the highway, that means you've got a higher voltage. Similarly, the current is the number of cars passing per second, but in actual physical terms, they actually measure the current in the number of electrons. Similarly, the voltage is represented by, if you're looking at the highway analogy, it would be the cars and how fast they're going. So if the cars are going faster, you have a higher voltage. Now, if you take the number of amps, and if you think about it, the wider your highway, the more cars can go through at a certain amount of time if they're all going at a similar speed. So that also means that if you have a higher current, you need a thicker wire in terms of electricity. And if you want to move a lot of cars, and if you can move them faster, you can actually have a thinner wire or a smaller highway, and you would have the same result. So, but as if cars are moving faster, it's similar to voltage, and the electrons are moving faster. This is an image which sort of explains the concept of volt. And this volt is the pressure, which is the speed, which is the one that's pushing the current, which is the electrons through the wire, and ohms are the unit of resistance, which is the amount of resistance towards the movement of the electrons. The thinner the wire, the more resistance you will have. Similarly, you could also have the analogy of water going through a pipe. The pressure of the water will define how fast the water moves through it, and that would be the voltage. The amount of water that's going through is going to be the amperage. The size of the pipe will define how much resistance there is, and the length of the pipe also will define the resistance. So the smaller the pipe, you would have more resistance, and in electrical terms, the ohms would be higher. If you multiply the voltage with the current, which is the speed and the amount of electrons moving through, you get something called power, which is the energy created. Actually, energy is not wattage. Wattage is connected to time. So when you have power, when you multiply power with time, you will end up with energy. Okay, power is, like we explained, if you multiply the current with the volts, you will get the power in watts. And it represents the total number of cars and the speed at which they're moving through the wire. Suppose you have an air conditioner. It will say something like it needs to 1,000 watts or 2,000 watts. In this case, we'll just assume it's like 1,000 watts. So if you've got 100 volts and you've got 10 amps of current moving at 100 volts, you will end up with 1,000 watts. You could also have 1,000 amps of current through a very thick wire and moving very, very slowly at 1 volt, and you will have the same amount of power going through that wire. Any combination of volts and amp which multiplied together to give you 1,000 watts is going to be 1,000 watts. Now usually we use 220 volts. So if you're trying to get 1,000 watts and the electricity is moving at 220 volts, how many amps would that be? So if you divide the watts, which is 1,000 watts, by 220 volts, you would get around 4.5 amps. So that is the amount of current you would need if you're running your air conditioner at 220 volts and your air conditioner needs 1000 watts of power. Now we shall define some other terms, and since some of the technologies are new and they're continuously changing, the terms are used differently depending on who you talk to. And see, the definitions we are going to give you are ours to the best of our knowledge. If you think you have got better definitions and you could help reduce the confusion, then you're most welcome to email me at harvard@atrc.net.pk and give me the definition which you think helps define these terms better, or in a way which helps reduce confusion in the market. Okay, the first item is an inverter. An inverter simply is an electronic device which converts direct current into alternating current. It is also called a power inverter, and simple inverters generally have an on-off switch and do not have something called a low voltage disconnect, which we'll define later. A rectifier or adapter is the opposite of, does the opposite task as an inverter. This thing converts AC power into DC power. This is very commonly used like a mobile phone charger, laptops, and because all of these devices use DC, and it's also used to convert AC to DC for battery charging purposes, because batteries usually have a plus and a minus in their DC. There's no such thing as an AC battery so far. Anyway, a battery charge controller is an electronic component used in devices to control the amount of electrical power which is used to recharge batteries. Batteries are like chemical devices that just don't operate like a normal electrical circuit, so they have to be taken care of. And the battery charge controller is required to make sure it doesn't overcharge, because after the battery is fully charged, there is no way the battery can stop the electric circuit by itself. So the battery charge controller will try to use voltage or temperature and other methods to estimate whether the battery is fully charged or not, and then it will stop the charging. Similarly, if you're using a battery, after the battery is completely drained out, it can reach a state where some rechargeable batteries it's not good for them to be completely discharged. And if you do that, for example, if you have a lead acid battery, which is common in cars and other lot of areas and is one of the most common batteries, if you discharge it completely, you actually sort of destroy the battery and it cannot be recharged again, or it's very hard to recharge it. And even if you do recharge it after discharging it completely, the performance of the battery will be almost negligible, sort of like you waste the battery. So for that, you need a circuit called a low voltage disconnect. This is basically a circuit which measures the voltage of a battery, and based on that it estimates if the battery is dangerously low, and when it reaches that level, it disconnects the battery from whatever device is using the battery. So it's sort of like, that's what's called a low voltage disconnect. It's to prevent batteries from failing. A UPS, which is an uninterruptible power supply, has several components. One is it has an AC to DC rectifier, which is used to charge batteries. It has a charge controller to make sure that the batteries are charged correctly. It has the capability to connect the load, which is the devices, appliances you're using that are through the UPS. It will connect the load directly to the grid, so it doesn't use the battery whenever utility power is available. If utility power fails, it's called the UPS, which is uninterruptible power supply, because it switches immediately the inverter on and starts converting DC power from the battery into AC power, so that the appliances seem to continue to work as if the electricity is still available. And it also has a low voltage disconnect, so if the battery goes down very low, the UPS will actually turn off to protect the battery. And an inverter has the UPS has an inverter to convert the DC power into AC from the battery. Now we come to a solar charge controller. Basically, solar panels that we showed you earlier, they provide different voltages and currents depending upon the amount of light that is falling on them. So a solar charge controller is a special device which uses the varying voltages and current from a solar panel to charge a battery. Okay, so that's a solar charge controller. This does have a low voltage disconnect circuit, but usually it's only for small loads, and it has terminals to connect the battery directly, and it uses the solar panels to charge the battery. The small low voltage disconnect circuit can in some cases be used to power larger circuits to find out if the battery is low or not. So that can be used to control the switching of normal inverters. A solar inverter is something that actually converts the solar DC power. The solar panels actually provide DC, which is direct current, and a solar inverter converts the DC and varying amounts of DC into AC, and it does not charge batteries. And there's another thing called MPPT, which is maximum power point tracking, which is something a solar inverter is most probably going to do. You could have some solar inverters which do not, but the chances of having them are lower. And a solar inverter does not synchronize its output of the AC output to the grid. A grid tie inverter is similar to a solar inverter, but it actually takes a solar panel energy and synchronizes it with the grid. So what happens is it sort of like merges the electricity with the grid electricity that's coming into the home, and it increases the voltage of its output a little bit more than the grid output. So what happens is the home will end up using the solar panel energy before it uses the utility power. So, and if the home is not using all of the energy that the solar panel and the grid tie inverter is offering, what will happen is some of the electricity will flow in reverse out of the meter into the grid, and some of the meters are designed to go in reverse and measure that difference, and that will actually help generate money for the house, because the meter will be actually going in reverse. So this is what it looks like. You've got solar panels, and this is a grid tie inverter. It powers electricity to the house, and since the voltage is higher, if the house doesn't use it, the voltage and electricity will actually go out of the meter into the grid, and the meter will go in reverse. Net metering is a method called where the buying price and the selling price is different. So what happens is you've got these spatial meters which are installed, and these spatial meters, like here in net metering, you would have this meter. It would measure how much of the electricity was used in this direction, and it will be billed accordingly, and the amount of electricity going back towards the grid will be counted separately, and it will be billed at something called a buyback price. The buyback price is usually less than the selling price. Now we come to off-grid inverters. Off-grid inverters are those which are based on solar panels. They've got batteries connected to them, they have a backup generator available, and they provide electricity to the home without any option for having a utility grid. These are also called standalone inverters, and they are used in areas where the grid is not available, or sometimes the grid is so far away that it's pretty expensive to get a wire to your home, and that's where these off-grid inverters are used. So this is what the design looks like. You've got solar panels, you've got a charge controller. The charge controller charges the batteries correctly, and the batteries are used by an inverter. You should have a low voltage disconnect option inside the inverter, because this is connected directly to the batteries. And the actually it does. The off-grid inverters do have a low voltage disconnect which you can program. So I mean, it's not an ordinary inverter, this is a off-grid inverter, so it will take care of the batteries. And you have got an optional generator which it can start in case the batteries run low and you are at night and the house needs more energy. Now we come to the hybrid solar inverter. This one is like a combination of grid tie and off-grid solar inverters. This one can connect a solar panel to the AC, store the extra in the battery for the night, and it can actually compensate for loads from the grid also. These are also called multi-mode inverters. This is what it looks like, where you've got a charge controller, you've got a battery bank, you've got an inverter, and you got the meter. Okay, so here you've got the solar panels, you've got the charge controller charging the batteries. This is your hybrid inverter, and the hybrid inverter can use some extra from the utility if it's available instead of the generator. And this is a cheaper option wherever the grid is available, so that way you actually have lower cost solar energy whenever the grid is not being used. And in case your load is higher at night, it saves on the battery costs, so you don't really need that much of a battery, and it sort of uses the utility as a battery. A variable frequency drive is an electronic device which is used to control the speed of electric motors. The other names for variable frequency drives are adjustable frequency drive, variable speed drive, AC drive, micro drive, inverter drive, and some people just call it a drive. The issue is that AC motors, if you change the voltage, it doesn't really affect the speed of the motor. The only way to change the speed of the motor is to change the frequency of the AC current that's going into the motor. And there is no easy way to transform AC current, so what the people do is they convert the AC through a rectifier into DC, and then the DC is converted through an inverter back into AC. But since you are creating the AC current in the inverter, you can select which kind of frequency you want, so that the component of rectifier plus DC bus and the inverter component combined is called a variable frequency drive. Usually variable frequency drives are designed to have an input of 3-phase AC. Some have a single phase AC input. They convert that to around 400 volts DC, and then they give it to their inverter portion, which converts it back into AC, but it knows what, based on the speed that is required, and that can change. It can change the frequency of the AC that's created. The DC bus, which is the middle portion of the variable frequency drive, has terminals which are available in case you have a huge DC power supply available to run the VFDs, but it requires and is designed to have a stable voltage. Some people connect solar panels to the terminals of the VFD DC bus, and they do that due to lack of knowledge about VFDs. A solar pump inverter is similar to a VFD, but it has extra components in it. One is that it has an MPPT, solar panel charge follower. That means it can find and track the maximum power point of a solar panel, so that will give it more efficiency if a solar panel is connected to this. Then it has a VFD component, which is the one that actually uses the DC bus. So the MPPT part takes a DC from the solar panel and manages that, and then it has a minimum voltage at which it will start, because it knows that solar panels in the morning will start at 0 volts and then they'll ramp it up. So, and it's dangerous to give a certain, below a certain amount of power. It's not good to give it to the AC motor due to the life reduction of the AC motor. So you need at least a minimum amount of power before you can provide it to the AC motor. So you've got the solar charge controller, then you've got the variable frequency drive component, and these combined together are called a solar pump inverter. Since a VFD is not designed to have MPPT, so even if you do somehow get the VFD running on a solar panel, you will get less efficiency, and secondly, you run the risk of destroying a VFD designed for AC input and not for solar panel input. Recently some VFD companies have started making solar pump inverters, and they still call them solar VFDs. So you have to be careful of what your VFD is. The old term is not SPI, the new term is solar pump inverter. So to make sure that your VFD can actually handle solar panels, look for the word solar or MPPT as a term inside the specifications. And if the input is only defined as 3-phase input or single-phase input, then you can assume safely that that is a real VFD and it's not really designed to have solar panels connected to it, and you run the risk of destroying the VFD if you misuse it. So in summary, we have discussed solar panels, cells, how panel specifications are defined, the difference between charge controllers and UPSs, what are inverters, what are variable frequency drives, what are solar pump inverters, and what is maximum power point tracking. I hope you found this presentation useful. If there are other topics related to energy or automation, you are most welcome to send an email, and we'll try to make presentations to explain and summarize what we know. Thank you. Here is the contact information in case you want it. Thank you for listening. Have a nice day.